Imagine a space rock the size of a small city, shaped like a cosmic rubber duck, hurtling through the universe at a staggering speed of over 135,000 kilometers per hour. Does that sound like science fiction? In reality, we're talking about Comet 67P/Churyumov-Gerasimenko, one of the most fascinating and studied objects in our solar system. This comet is not just a simple icy body, it is a time capsule from the early solar system, holding secrets about the formation of planets and even the origins of life itself. As we delve into the wonders of 67P, we'll uncover the mysteries that have captured the imagination of scientists and space enthusiasts alike. Buckle up as we embark on this extraordinary journey through the cosmos. Today, we're setting sail on an extraordinary journey to explore Comet 67P/Churyumov-Gerasimenko. We'll dive deep into why this comet is so special, what groundbreaking discoveries we've made through its study, and how it's revolutionizing our understanding of the solar system's formation. From its unique duck-like shape to its complex composition, 67P is more than just a celestial object. It's a key to unlocking the history of our cosmic neighborhood. With insights from the Rosetta mission, which orbited and landed on this comet, we'll reveal how the data gathered is reshaping our theories about where we come from and how our solar system evolved. So join me on this cosmic adventure, and let's discover together the marvels that Comet 67P has to offer. If you're enjoying this cosmic journey, don't forget to hit the like button and subscribe to Exploring the Universe for more incredible space stories and discoveries. Let's continue to explore the wonders of the universe together. The story of Comet 67P/Churyumov-Gerasimenko begins in 1969, when it was first discovered by two Soviet astronomers, Klim Churyumov and Svetlana Gerasimenko. They were examining photographic plates taken from the Kiev University Observatory in Ukraine when they noticed a fuzzy object that was not present in previous images. This marked the first identification of what would become one of the most studied comets in the solar system. At the time of its discovery, the significance of 67P was not immediately apparent. It was just one of many comets, roaming the solar system largely unnoticed. However, the comet's path brought it closer to the Sun, and as it did, it began to display the characteristic glowing coma and tail that make comets so captivating. Fast forward to 2014, when 67P shot to fame in the astronomical community. The European Space Agency launched the Rosetta mission in 2004 with the ambitious goal of studying a comet up close. After a decade-long journey through space, Rosetta arrived at 67P, becoming the first spacecraft to orbit a comet. This milestone was a significant achievement in space exploration, showcasing human ingenuity and our relentless pursuit of knowledge about the cosmos. The mission took another groundbreaking step when the Philae lander, carried aboard Rosetta, successfully touched down on the comet's surface on November 12, 2014. This historic event marked the first time a human-made object had landed on a comet, and it opened the door to unprecedented scientific discoveries. Through the Rosetta mission, scientists were able to gather invaluable data about the comet's composition, structure, and behavior as it interacted with solar radiation. The findings have not only enhanced our understanding of comets, but have also provided insights into the early solar system and the building blocks of life on Earth. As we delve deeper into the characteristics and significance of 67P, we will uncover how this once ordinary comet became a focal point in the quest to unravel the mysteries of our universe. One of the most striking features of Comet 67P/Churyumov-Gerasimenko is its peculiar shape, often likened to a rubber duck. This bizarre form has captivated scientists and space enthusiasts alike, offering valuable insights into the comet's formation and behavior. The rubber duck shape of 67P consists of two distinct lobes connected by a narrow neck. The larger lobe, which forms the body of the duck, measures about 4.1 kilometers across at its widest point. The smaller lobe, forming the head, is approximately 2.6 kilometers wide. This unusual configuration is believed to be the result of a low-velocity collision between two smaller bodies, rather than being carved out of a larger object. To visualize this formation process, imagine taking two snowballs of different sizes and gently pressing them together. This low-speed impact scenario is supported by the comet's low density and high porosity, suggesting that the original bodies were only lightly compressed when they merged. The unique shape of 67P has significant implications for its behavior and characteristics. The irregular shape creates a complex gravitational field. This means that the force of gravity varies across the comet's surface, which affects how dust and gas are distributed and ejected. 67P's shape influences its rotation. The comet spins on its axis once every 12.4 hours, but this rotation is not uniform. The irregular mass distribution causes wobbling and precession, similar to a spinning top as it slows down. As the comet approaches the Sun and heats up, the irregular shape affects how and where gas and dust are released. Some areas, particularly in the neck region, show more activity than others, creating jets of material that contribute to the comet's coma and tail. The narrow neck connecting the two lobes is a point of particular interest. Scientists have observed cracks and have speculated about the potential for the comet to split at this point in the future. The shape has led to a diverse topography, with cliffs, depressions, and flat plains. This varied landscape affects how sunlight is absorbed and reflected, creating temperature differences across the surface. Understanding 67P's shape has been crucial for mission planning. For the Rosetta mission, navigating around the comet and finding a suitable landing site for the Philae lander required detailed mapping and consideration of the comet's irregular form. Comet 67P/Churyumov-Gerasimenko, like most comets, is often described as a cosmic dirty snowball. However, this simplistic description belies the complex composition and structure that makes 67P a fascinating subject of study. Thanks to the unprecedented close-up observations made possible by the Rosetta mission, we now have a much more detailed understanding of this celestial object. The bulk of 67P is composed of a mixture of ices, dust, and rocky material. The ices are predominantly water ice, but also include more volatile compounds such as carbon dioxide, carbon monoxide, methane, and ammonia. The dust component consists of silicates, sulfides, and organic compounds. This mixture is not uniformly distributed throughout the comet, leading to a heterogeneous structure. One of the most surprising discoveries about 67P is the nature of its surface. Unlike the bright reflective surface one might expect from a snowball, 67P's surface is remarkably dark. It reflects only about 4% of the light that hits it, making it darker than coal. This dark coloration is due to a layer of organic compounds coating much of the comet's surface. The surface of 67P is covered by a crust of complex organic molecules. These carbon-rich compounds are thought to have formed through the interaction of simpler molecules with solar radiation and cosmic rays. This organic layer is of particular interest to astrobiologists, as it may provide clues about the role comets played in delivering organic compounds to early Earth. Rosetta's measurements revealed that 67P has a remarkably low density, about half that of water. This suggests that the comet has a highly porous internal structure, with some scientists describing it as a fluffy aggregate of smaller particles rather than a solid body. Evidence from Rosetta's observations suggests that 67P has a layered internal structure. These layers might be the result of the comet's formation process or subsequent evolution as it orbits the Sun. Certain areas of 67P, particularly around the neck region connecting its two lobes, show more activity than others. As the comet approaches the Sun, these regions release jets of gas and dust, contributing to the formation of the comet's coma and tail. One of the most exciting discoveries was the detection of complex organic molecules, including amino acids like glycine, on 67P. This finding supports the theory that comets may have delivered some of the building blocks of life to early Earth. The composition of 67P is not uniform. Different regions of the comet show variations in the ratios of ice to dust and in the types of molecules present. This heterogeneity provides clues about the comet's formation and evolution. As 67P approaches the Sun in its orbit, the increasing heat causes some of its volatile components to sublimate directly from solid to gas. This process is responsible for the comet's activity and contributes to its gradual evolution over time. In a surprising discovery, Rosetta detected significant amounts of molecular oxygen in 67P's coma. This finding challenges some existing theories about comet formation and composition. The detailed study of 67P's composition and structure has revolutionized our understanding of comets. It has shown that these celestial bodies are far more complex and diverse than previously thought. The findings from 67P not only shed light on the nature of comets themselves, but also provide valuable insights into the composition of the early solar system and the potential role of comets in the origins of life on Earth. The Rosetta mission, led by the European Space Agency, stands as one of the most ambitious and groundbreaking space exploration endeavors in history. It marked the first time humanity successfully orbited a comet and landed a probe on its surface. This feat can be likened to landing a refrigerator-sized drone on a stadium-sized object hurtling through space at mind-boggling speeds. Launched on March 2, 2004, Rosetta embarked on a decade-long journey through the solar system to reach its target, Comet 67P/Churyumov-Gerasimenko. The mission consisted of two main components: the Rosetta orbiter and the Philae lander. Rosetta's path to 67P was far from straightforward. To gain enough speed to catch up with the comet, The spacecraft performed a series of gravity assist maneuvers, including 3 Earth flybys and 1 Mars flyby. This complex trajectory took Rosetta on a 6.4 billion kilometer journey before it finally reached its destination in August 2014. On August 6, 2014, Rosetta became the first spacecraft to rendezvous with a comet, entering orbit around 67P. This achievement alone was a major milestone in space exploration, allowing for unprecedented close-up observations of a comet. Over the next few months, Rosetta meticulously mapped 67P's surface, searching for a suitable landing site for Philae. This task was complicated by the comet's irregular shape and varied terrain. On November 12, 2014, history was made when Philae separated from Rosetta and began its descent to 67P's surface. The landing, however, didn't go entirely as planned. Philae first touched down almost exactly on target, but its harpoons failed to fire to anchor it to the surface. Due to the comet's extremely low gravity and the failure of the anchoring system, Philae bounced twice, traveling about 1 kilometer over 2 hours before coming to rest. Philae ended up in a shadowy area, limiting its ability to recharge its solar batteries. The difficulty of this landing cannot be overstated. Consider these factors. 67P measures only about 4.3 kilometers at its widest point. The comet was moving at speeds of up to 135,000 kilometers per hour relative to Earth. The gravity on 67P is about 1/10,000th that of Earth. The surface features were largely unknown before the mission. Despite the challenging landing, Philae managed to conduct about 60 hours of scientific operations before its primary battery was depleted. It briefly reawakened in June 2015 as the comet moved closer to the Sun but soon fell silent again. While Philae's mission was short-lived, Rosetta continued to orbit and study 67P for 2 more years. It observed the comet's behavior as it approached and then retreated from the Sun, providing invaluable data about cometary activity. On September 30, 2016, ESA deliberately crash-landed Rosetta onto 67P's surface, ending the mission. This controlled descent allowed for extremely close-up observations in the final moments of the mission. The Rosetta mission and Philae's landing revolutionized our understanding of comets. It provided unprecedented data on cometary composition, structure, and behavior. The mission's success paved the way for future small-body exploration missions and demonstrated the feasibility of complex maneuvers in deep space. The study of Comet 67P/Churyumov-Gerasimenko has far-reaching implications that extend beyond pure astronomical interest. The knowledge gained from this mission is contributing to various fields of science and technology, offering practical applications and insights into our cosmic origins. Comets like 67P are often referred to as cosmic time capsules. They contain pristine material from the early solar system, preserved in a deep freeze for billions of years. By studying 67P's composition, we gain direct insight into the conditions and materials present during the formation of our solar system. The analysis of 67P's structure and composition helps us understand the nature of the building blocks that eventually formed planets. This knowledge is crucial for developing and refining models of planetary formation. The study of 67P's water composition, particularly its deuterium-to-hydrogen ratio, provides clues about the potential role of comets in delivering water to early Earth. The Rosetta mission required unprecedented precision in deep space navigation. The techniques developed for rendezvousing with a small, irregularly shaped object moving at high speed are now being applied to other space missions. The challenges faced during Philae's landing have led to improvements in landing systems for future small-body missions. This includes advancements in anchoring mechanisms and strategies for dealing with low-gravity environments. Rosetta's decade-long journey provided valuable experience in managing long-duration space missions, including spacecraft hibernation and long-distance communication. The distance between Earth and 67P necessitated a high degree of autonomy for both Rosetta and Philae. The AI and decision-making algorithms developed for this mission are pushing forward the field of autonomous robotic exploration. The techniques developed for operating in the harsh, low-gravity environment of a comet are applicable to future missions to asteroids, moons, and other small bodies in the solar system. The discovery of complex organic molecules on 67P, including amino acids, provides support for the theory that comets may have delivered some of the building blocks of life to early Earth. Understanding the conditions on 67P informs research into extremophiles and the potential for life in harsh cosmic environments. Studying how 67P changes as it approaches the Sun improves our understanding of comet behavior. This knowledge is crucial for predicting the paths of potentially hazardous comets and developing strategies for planetary defense. The study of 67P's surface properties, particularly its dark, organic-rich crust, could inspire the development of new materials for use on Earth, such as ultra-black coatings or highly porous insulations. Comets like 67P contain trapped gases from the early solar system. Analyzing these can provide insights into the ancient solar environment, contributing to our understanding of long-term climate processes. The Rosetta mission captured public imagination, providing numerous opportunities for science education and public engagement with space exploration. The success of the Rosetta mission demonstrated the power of international scientific collaboration, setting a model for future large-scale space exploration projects. The study of 67P contributes to our understanding of the origins and evolution of our solar system, impacting our perspective on humanity's place in the cosmos. Dr. Catherine Altwegg, the principal investigator of the Rosetta instrument on the Rosetta mission, provided a pivotal insight into the significance of 67P. Her statement, "67P has surprised us with its complexity. We found organic molecules that we had never detected on a comet before, including glycine, an amino acid essential for life," encapsulates the groundbreaking nature of the discoveries made during the Rosetta mission. Dr. Altwegg's mention of 67P's complexity underscores how the comet defied many pre-existing expectations. Prior to Rosetta, our understanding of comets was largely based on remote observations and limited flyby missions. 67P revealed a level of structural and compositional intricacy that was previously unimagined. This complexity is evident in the comet's irregular shape, varied surface features, and heterogeneous composition. It suggests that comets are not simple dirty snowballs, but rather sophisticated celestial bodies with rich histories and diverse characteristics. The detection of previously unobserved organic molecules on 67P is a landmark achievement. It expands our understanding of the chemical diversity present in the early solar system. These organic compounds range from simple molecules to more complex ones, including aromatic hydrocarbons, alcohols, and nitrogen-containing compounds. Each of these discoveries provides new insights into the chemical processes occurring in space. The identification of glycine on 67P is particularly noteworthy. Glycine is the simplest amino acid and a crucial building block for proteins, which are essential for life as we know it. This discovery supports the hypothesis that comets could have delivered some of the precursor molecules necessary for life to early Earth. It bridges the gap between cosmic chemistry and the origins of biological processes. The presence of complex organic molecules, especially glycine, on 67P lends credence to the theory of panspermia, the idea that life or its precursors could be distributed throughout the universe by celestial bodies like comets and asteroids. It suggests that the ingredients for life may be more common in the solar system and beyond than previously thought, expanding the potential for habitability on other worlds. Dr. Altwegg's statement reflects how the study of 67P has transformed our understanding of comets. These bodies are now seen not just as remnants of the solar system's formation, but as complex, evolving entities that play a crucial role in cosmic chemical processes. The discoveries on 67P have prompted a re-evaluation of cometary models and their potential influence on planetary evolution. The ability to detect these complex molecules speaks to the sophistication of the instruments aboard Rosetta, particularly the Rosetta instrument. It showcases the advancements in space-based analytical chemistry. These findings have opened up new avenues for research in astrochemistry, astrobiology, and planetary science. They raise questions about the prevalence of organic compounds in other comets and small bodies in the solar system. The discoveries on 67P bridge multiple scientific disciplines, from astronomy and chemistry to biology and geology. This interdisciplinary nature highlights the broader impact of cometary research on our understanding of the universe and our place in it. Discoveries like the presence of glycine on 67P capture public imagination and interest in space science. They provide tangible connections between cosmic processes and the fundamental questions of life's origins. The complexity of 67P and its organic inventory challenge us to reconsider our perception of comets, the solar system, and potentially, the uniqueness of life on Earth. The study of Comet 67P/Churyumov-Gerasimenko has revealed a plethora of fascinating and unexpected characteristics. These discoveries not only capture our imagination but also provide valuable scientific insights. Let's explore some of the most intriguing facts about this cosmic wanderer. 67P sings. The Rosetta probe detected magnetic oscillations coming from the comet which, when converted to sound, resemble an alien hum. These songs are actually plasma waves generated by the comet's interaction with the solar wind. The comet's activity creates a complex magnetic environment that oscillates at frequencies between 40 to 50 MHz. This phenomenon provides valuable information about the comet's magnetic field and its interaction with the solar environment. It's a unique way to study cometary plasma dynamics. Another fascinating fact is that 67P loses about 1 meter of its surface every orbit around the Sun due to ice sublimation. It's as if the comet is slowly dissolving in space. As 67P approaches the Sun, its icy components heat up and transition directly from solid to gas, a process called sublimation. This results in the characteristic coma and tail of the comet. The loss of 1 meter per orbit is significant given the comet's size, about 4.3 kilometers at its widest. This rapid change allows scientists to observe geological processes in real time that would take millions of years on Earth. This continuous loss of material means that comets like 67P have finite lifespans. It also provides insights into how comets evolve over time and how long they can survive in the inner solar system. 67P's distinctive shape, often compared to a rubber duck, is not just quirky but scientifically significant. It's believed to be the result of two smaller comets merging in a low-speed collision. This shape influences the comet's rotation, gravity field, and the distribution of its active regions. A day on 67P lasts about 12.4 hours, much shorter than Earth's. This rapid rotation contributes to the comet's complex thermal and outgassing patterns. Despite being composed largely of ice, 67P's surface is incredibly dark, reflecting only about 4% of the light that hits it. This is due to a coating of organic compounds and is darker than coal. The comet's surface features numerous large pits, some over 100 meters wide and deep. These are thought to be sinkholes formed by the sublimation of subsurface ice. As 67P orbits the Sun, it experiences seasons. The northern and southern hemispheres take turns facing the Sun, leading to varying levels of activity across the comet's surface. 67P is a veritable organic chemistry laboratory. It produces complex organic molecules, including some never before detected in comets, through reactions driven by solar radiation. Despite its rocky appearance, 67P has a density lower than water, suggesting a highly porous internal structure. It's more akin to a cosmic dust bunny than a solid rock. Rosetta detected several outburst events on 67P, sudden releases of dust and gas that could be likened to comet quakes. These events reshaped parts of the comet's surface. The water on 67P has a different deuterium to hydrogen ratio than Earth's water, challenging the theory that comets like 67P were the primary source of Earth's oceans. Molecular oxygen was detected in 67P's coma, surprising scientists as O2 is highly reactive and was not expected to survive from the solar system's formation. The study of comets, particularly 67P/Churyumov-Gerasimenko, has opened up new frontiers in space exploration and planetary science. However, it has also presented scientists with a host of challenges and exciting possibilities for future research. One of the biggest current challenges is understanding how comets like 67P evolve over time. Scientists are working on advanced computational models to predict how these celestial bodies will change in the coming decades and centuries. Key aspects of this challenge include modeling the rate of mass loss due to sublimation, predicting changes in orbital dynamics, understanding the structural evolution of the comet's nucleus, forecasting changes in surface features and activity patterns. Observations of 67P and other comets have revealed significant diversity in cometary compositions and behaviors. Developing a unified theory that explains this diversity while accounting for common origins is a major challenge. While we've detected complex organic molecules on 67P, understanding the full extent of its organic inventory and the processes that create these compounds remains a challenge. Discoveries like molecular oxygen in 67P's coma and the comet's magnetic song have challenged existing models. Explaining these phenomena within the framework of cometary physics is an ongoing task. Enhancing our ability to study comets from Earth-based or near-Earth observatories is crucial, especially given the rarity of close-up missions like Rosetta. In the future, space missions may attempt to collect samples from comets and bring them back to Earth for detailed analysis. Imagine having a piece of a comet in a terrestrial laboratory. This would allow for precise dating of cometary material, detailed analysis of organic compounds, study of isotopic ratios with unprecedented accuracy, examination of the physical structure at microscopic levels. Future missions might involve placing long-term observatories in orbit around comets, allowing for continuous monitoring over multiple orbits. Comets could serve as potential resources for future deep space missions, providing water, oxygen, and organic compounds. Research into the feasibility of cometary mining may become more prominent. Advances in propulsion and navigation might enable missions that visit multiple comets, allowing for comparative studies. AI and machine learning could revolutionize data analysis, potentially uncovering patterns and relationships in cometary behavior that human researchers might miss. As our ability to detect smaller bodies around other stars improves, the study of comets in other solar systems may become possible, providing insights into the universality of cometary processes. Future cometary research is likely to involve increased collaboration between astronomers, chemists, geologists, and biologists, especially in the context of astrobiology and origin of life studies. Future missions may incorporate more opportunities for public participation, from helping to analyze data to potentially controlling instruments on distant spacecraft. The development of more sophisticated computer models, possibly utilizing quantum computing, could allow for more accurate predictions of cometary behavior and evolution. As our understanding of comets grows, so too might our ability to predict and potentially mitigate cometary impacts on Earth, contributing to planetary defense strategies. Comet 67P/Churyumov-Gerasimenko is far more than just a duck-shaped space rock. It serves as a portal to our solar system's distant past, a natural laboratory for studying organic chemistry in space, and a milestone in our ability to explore distant celestial bodies. Each discovery about 67P brings us a step closer to understanding our own cosmic origins. The journey of discovery with 67P is far from over. As we continue to analyze data from the Rosetta mission and apply new analytical techniques, we can expect further revelations about the nature of comets, the early solar system, and potentially the origins of life itself. I hope this journey through the fascinating world of Comet 67P/Churyumov-Gerasimenko has expanded your horizons as much as it expands mine with each video. If you want to continue traveling through the cosmos with me, don't forget to subscribe to the channel and turn on notifications so you don't miss any space adventure. Share this video with friends who also love the universe, and let me know in the comments which aspect of comets you want me to explore in more depth. Your engagement helps shape the content of this channel and fuels our shared exploration of the cosmos. If you enjoyed this cosmic journey, please give this video a thumbs up. Your likes help more space enthusiasts discover our growing community of cosmic explorers. For those of you hungry for more celestial knowledge, check out the playlist linked in the description. It's full of videos diving deep into other fascinating objects in our solar system and beyond. Remember, your support through likes, comments, and shares not only helps this channel grow but also contributes to spreading scientific knowledge and wonder about our universe. Until the next video, keep looking up and remember, in the universe, curiosity is our fuel. Thank you for joining me on this cosmic adventure, and I'll see you in the next exploration of the wonders of space.